opportunity. I'm Ritsuki Morohoshi from University of Tokyo, Japan. My research is about the effect of stress field and trip behavior and its influence on fracture behavior of commercial stainless steel at cryogenic temperature. These are my content. Mostly we talk about experiment and FBM analysis to model the multisthetic transformation. Firstly, I'd like to tell you some background of it. The ultimate purpose is that the fracture assessment of large liquefied hydrogen storage tank. This is it. And which is made by the arsenic stainless steel. And to approach this aim, we need to model the finite element analysis on the fastened fracture area of stainless steel on the hydrogen embodiment in 20 Kelvin, which is liquefied hydrogen temperature. And let me explain briefly about the assumed fracture area. We assume that fracture happened when an earthquake, because there's a lot of earthquake in Japan. So, and there's a point of it, the joint between the annual plate and sidewall. So this is the yellow bit. Yes. So as a side note, I want to briefly tell you that how much of the stress structurality it is on the notch tip. The graph shows that it's around 1.5, which is very high. And as I mentioned before, to do the finite element analysis on such condition, it's impossible to do based only on the previous studies, because there's maybe two reasons why. The first is that it's unclear that how related to the loading state, which including stress structurality and multisthetic transformation. The second is that it's also unclear that how related loading state and hydrogen embodiment. So we need to break down more my scope of my research a little more. This is what I mentioned before. And because of the difficulty to use liquid hydrogen so casually, so we firstly want to predict the stress strain curve on the assumed fracture area of garment stainless steel under 77 Kelvin, which means that liquefied nitrogen. And this statement have two factors. The first is the second method. It is the kind of method that to simulate this stress strain curve of dual phase metal. And I would like to omit the details info. And the second one is the prediction of the relationship between the multisthetic transformation and the strain on the high stress structurality of stainless steel and on the liquefied nitrogen. This is what I wanted to say. And this is a kind of graph that shows my contents. This is what I already mentioned it. And this is the goal of my research. It is very high stress structurality. And to approach this, we firstly conduct the experimental evaluation from a relatively low stress structurality and extrapolate it to it by using the finite element analysis. And we need to note that this procedure was taken under every constant value of strains and taken by some materials. And first, I want to talk about the experiment. First, I need to note that this is still ongoing research, so that I can tell you the global result of it. So I just tell you the part of it. So first, I want to tell you about the comparison of metals There's a very convenient index that to show the ease of multi-static transformation called MD30. This is the definition of it. Briefly, it's the higher the index is, it's getting more easily to get nucleate multi-site. And I conducted the two kinds of experiment for every 4 types of stainless steel. And these are chosen by the index of MD30, could vary. And the typical round both specimens are used for getting multiple samples just by just tensile one test, as shown in this graph. And the multi-static content was measured by USD method. This is the result. X-axis shows the equivalent plastic strain at 77 Kelvin, and the y-axis shows the fraction of martensite. And the words aligned to each series show that the kind of metals and MD30. Accordingly, the MD30 is still the effective index to show the tendency of multi-static transformation under 77 Kelvin. And regarding 304 and 304L, about half of the transformation occurred even at the zero strain. On the other hand, regarding the 310S, a low multi-static transformation occurred in the interior area. Next, I want to tell you the comparison of stress structurality. These are the specimens. The left one is for the uniaxial tension. Right one is for the uniaxial compression. And this is the result of it. These are stress strain curve. And I measured the EVSD method, EVSD analysis on this area. And this is the inspected area. This is a phase graph of the uniaxial tension. Red shows the martensite and green shows the austenite. And so a little bit blue shows the epsilon martensite. And it says that about half of the 50% of martensite nucleates. On the other hand, this is the uniaxial compression test. There's only 10.8% of martensite transformation occurs. So it means that on the fixed truth strain, we can say that the higher the stress structurality is, the more likely to be nucleated martensite. And I'm going to tell it's about the FM analysis. First, I need to depict some characteristic of martensite to model. Generally, martensite, the driving forces of stress in this martensitic transformation could be explained as the following. It's comprised of 2 factors. It's kind of the shear stresses, shear energy, and more like expansive energies. My model of martensitic transformation focuses only on expansion because we don't need to model the habit planes. Habit planes, it's slightly complicated to be modeled accurately. And we did it by stress control. It's because it makes stable. It makes stress structurality stable in entire stimulation. To describe the plastic displacement by stress control, work hardening is necessary. So The work hardening fitted by the Swift equation of 304 and under the 77 Kelvin is used. And this is an example of the procedure of Earth simulation. For simplicity, a two-dimensional model is used, and the plane stress and plane strain were conducted. And the first, the green plots show the oscillate assumed, and the white one is the transformation region, which is first series oscillate but going to be multi-site. And this is a uniaxial example. And then we apply the 3% equivalent strain surface forces. And then fix the displacement and expand it here 9%. The reason why the 9% is that we approximate the multistatic transformation as face center cubic to body center cubic. And we randomly generate period applied stress. It's just a uniaxial, but we randomly made a lot of kind of things, and about 360 times per the patterns. And we also need to fabricate the new index to simulate it, to substitute as a substitution of driving force for multistatic transformation. Since the multistatic transformation is a reversal process under the fixed temperature, so it's reasonable to substitute the trend of multistatic transformation to the reduction of potential energy. And in this system, there's the only, the elastic strain energy is the only potential energy. So we checked if the amount of multistatic transformation is predictable by using this potential energy. This is the example of how the simulation goes. And this is a typical example of it. The x-axis shows the steps, and the y-axis shows the potential energies. And there is a histogram that shows each standard deviation of stress structurality and load parameter. We can say that it's very stable on entire series of simulations. And this is the result of it. We can say that let me explain how to see the graph. X-axis shows the load parameter, and the y-axis shows the stress structurality, and the colors mean that how the reduction of the potential energy. The lighter it be, the more reduction occurs. So, as a result, this indicates the correlation between simulation and experiment. But however, the correlation is just a qualitative point of view. And in fact, according to some talk, the driving force, the chemical driving force of multistatic transformation of 316L under 77 Kelvin, the energy value is about 100 times as much as the simulation results. So it's very small value compared to this chemical driving force. So which means it's not consistent. So in future work, I want to quantify it. This is the conclusion of mine. Thank you for listening.
Thank you very much for your presentation. The paper is now open for discussion, please. Yes, please.
A short question. Have you, because you made some comments but I haven't got it, have you considered incorporated in your model the volumetric change during the martensitic transformation?
Yes.
Okay, good.
Any more questions or comments? Is the toughness also important for your research?
Yes, because multi-static has more hardening,
Yeah.
right?
And you are dealing with cryogenic temperatures also, yeah?
Yes, yes,
Yeah.
yes.
Yeah. And the induced martensite, we know that if we bend, if we roll, we transform austenite because you are using austenitic stainless steel.
Yeah.
You will transform some in martensitic. So you are saying that you have triaxial stresses, and you should have your application is a tank storage. Is a tank storage.
Yeah.
So the number of cycles per day that you are you
Soon.
applying to the tank?
The time of cycle. I've never tried to explore how much
Yes, I understand.
cycle in the bed. It seems that we need to open the tank to pick some liquefied hydrogen outside of it. So 5
Right.
per day,
Yeah.
I guess.
Okay, thank you very much.
Thank you.
Okay, thank you very much once again.